Good morning. So thank you for coming back. Today we're going to talk about Chapter 2.4 on conditional probability. This is a very interesting topic that a lot of students got confused. Why? Because we're not used to think about a pair of events. So let me give you an example here. Let's say we throw a die and we ask about what is the probability of getting a 5. Okay, that's pretty easy, 1 over 6. Now I give you another event. We say that what is the probability of getting numbers bigger than or equals to 4? The probability of getting numbers bigger than or equals to 4, 3 over 6, right? 4, 5, and 6. Now, think about the following situation. I tell you that you throw a die, and it is a number that is bigger than or equals to 4. I tell you that. Okay? So this statement is already given to you. And then I ask, within this subset, what is the probability of getting a 5? What is that? 1 over 3. Okay, it's not 1 over 6. It's 1 over 3. Okay, and everyone understands this kind of concepts, right? There is an event that happens before the second event. There's a relationship between the two. And I'm restricting myself to a smaller subset. I'm considering that smaller subset, I'm considering event inside that smaller subset. And that's called the conditional probability. I'm conditioning myself on a smaller subset of events, and then I'm considering another event within the subset. Now, this thing can get pretty nasty, as you can imagine, because you can have many different conditions, and then you have many different events, and which one condition on which, and they start to overlap, and then all of a sudden it becomes a mess. Okay? But if you ever get confused about what is conditional probability, go back to this example. Okay, you throw a die, and then there is a subset of conditions that you're considering. Within the subset of conditions, you consider an event. Okay? And the way to think about this is that you're changing the sample space in some sense. Okay? Originally, when you try to throw a die, you get a 5. The sample space is from 1 to 6. It's every 1. But now, when you're given a subset of conditions, that subset of conditions will define the sort of the new sample space. Okay? So think in this way as we are navigating through this chapter. Conditional probability. Okay, so let's get started. What is conditional probability? As the definition goes, the conditional probability is really the ratio. Okay, so this is the definition of conditional probability. There's a notation, A given B. So there are two events, A event, B event. Now let's associate A is the event getting a 5. B would be the event getting numbers bigger than or equals to 4. Okay, A and B. B is the condition that is given to you. So A given B, right? B has happened. What is the probability that A will also happen? So that is the meaning of this conditional probability. And it has a definition. The definition is this ratio of the probability of A intersecting with B divided by the probability of B. Now, at the first glance, of course, we cannot really comprehend what's going on the right-hand side. But at least I want to make sure that you get the picture. Right? You have a big set, and then you're looking at a subset. Inside the subset, you're looking at event, and then you're measuring the probability with respect to the condition that you're living on. All right, so now let's take a couple minutes to try to understand this definition, and then we can go back to the example we discussed how we're going to use this conditional probability. Okay, so on the right-hand side of this equation, you see a ratio. You see the ratio. It is a ratio of the intersection of A and B divided by the probability of B. Let's draw a picture, okay? Without touching all these equations, let's draw a picture. Let's say you have the sample space, which is the set that contains everything. And then now let us draw a set A. There is a set B. Okay, A being the set that can, it would be getting a 5, right? B would be the probability of getting bigger than or equals to 4, right? So in this case, it would be a proper subset. But let's imagine in general where you have two subsets, A and B. They do overlap. The stuff on the right-hand side, it is a ratio. Okay, it is a ratio. This ratio is measuring A-intercept B, which is this area, relative to B. Okay, it is measuring the probability of A and B relative to B. Okay, so now what is the difference between this and another quantity? The other quantity would be probability of A and B divided by the probability of omega. Okay, now you should look at these two equations. Here, yes, both the numerators, they are looking at A-intercept B. But then the denominator for the conditional probability, it is B. There's another thing, this is the omega, and they're different. Pictorially, what is the thing going on the right-hand side? Pictorially, what is going on the right-hand side is that you still have A, you still have B, and now you're looking at A-intercept B, right? So it's the same thing. But then the denominator is the entire sample space. So that is the ratio. Okay? So now, what is this? This is just A and B. Because the denominator is just 1, right? So this is A and B. I am only looking at the intersection of A and B. Okay, so that is the meaning of this quantity here. Here I'm looking at not just A and B, but A and B with respect to the condition that I am looking at, which is B. By looking at this picture, you can clearly see that A given B, would it be the same as B given A? Okay, so think about it. A given B versus B given A. Getting confused? Right? So A, probability A given B versus probability of B given A. Are they different or are they the same? Okay, excellent point. Okay, it depends whether they're the same size. Assume that they're different size, then we can pretty much say that they're different. Okay, they're very different. Fundamentally, why are they different? Because yes, on the numerator you're still looking at intercept B. Fine. Okay, you're the same. But then the denominator, the condition that you're posing, relative to that condition, one is relative to A, the other one is relative to B. Let's say A is bigger set than B, then the probability of A given B and B given A will be different. Right? So that's a logic here. Without doing any calculation here, by just looking at the picture, you should have a sense of A given B is not the same as B given A. Okay? That's the first confusion that a lot of students get. Okay? A given B, B given A, condition on something, something, condition on something else. What's going on? Think about there's a relationship going on between the two events. One defines the condition, the other one defines the event, and then you're looking at the ratio between the two. All right, so this is just another illustration of the situation. So this is A given B, this is A given B condition on B. So you're looking at this intersection over the set B. Let's look at a few examples to make sure that we understand. This is a more like a subjective example, okay? So, event A, for some reason, you want to eat 2 burgers. Event B, for some reason, you finish a football game. Okay? So the probability of A is that it is the probability that you eat 2 burgers. Now, that could be some numbers. Pretend that you really like burgers. Go to Burger King, you get 2 burgers for a coupon, whatever. Certain probability. Okay? B is that you just finish a football game. Now, of course, the football game schedule is according to some schedules, right? So the probability that we finish a football game, it will be some number. So we can measure. So there are 2 different events. Okay, so there are 2 different events. Now, they could overlap, right? Now, you can look at the probability that you just finish a game and you eat 2 burgers. That can happen. Okay, so you can look at the intersection of these 2 events, and that's called A intercept B. Now, that is going to be a smaller probability than the following one. The following is that you eat 2 burgers given that you just finished a game. Now, that can be high probability. Why? Well, I can make up some subjective examples. Perhaps you're too happy, you win the game. Or it could be that you're too hungry, you want to eat more. Right? So that is going to be a higher probability according to my subjective guess. Right? Now, you may disagree with me, but according to my logic, this is going to be a higher probability. And why? It's because this is going to be the probability of A intercept B divided by the probability of B. And here it's just be a probability of A intercept B divided by probability of omega. This one has to be a bigger number. So whenever you see 2 events, okay, one is a conditional event, the other one is unconditional event, very likely this unconditioned event will have a smaller probability than this conditioned event. Just because that the denominator that you're looking at, this is P omega, the other one is PB. Let's work on a little bit more concrete example. So numbers, right? Let's throw a die, and you have event A getting a 3, event B getting odd numbers. Let's calculate probability of A given B and B given A. Are they the same? Let's do it. You have an idea? Okay, so let's try that, okay? So the probability of A given B, okay? Probability of A given B. Let's don't use the formula. Just think about it. What is the condition? The condition is that I have 6 numbers, but I'm restricting myself to 3 numbers. Odd numbers, right? 1, 3, and 5. That's what we mean, okay? So I'm already constraining myself to a subset that contains 3 numbers. And I'm asking, what is the probability of getting that number 3? So that probability has to be 1 over 3 without following any formula. Let's read 1 over 3. Is it okay? Okay. Now, if we want to plug into the formula, that's also okay because it will be probability of A intercept B divided by the probability of B. Probability of A intercept B is the probability of getting a 3. This is the probability of getting a 3. And then the probability of B is 1, 3, and then 5. So this is 1 over 3. So the operation here is just a set operation. I'm not doing any probability. Until here, I just calculate 1, 2, 3. So there are 3 events in the denominator, 1 event in the numerator, so it's 1 over 3. How about probability of B given A? Mm-hmm. So 1 is a 1. Okay, do you agree? Yeah, 1. Okay, so let's again don't do any calculation by this formula, right? So the suggestion here is that you already get a 3. You already get a 3. I tell you that you get a 3. And then what is the probability that this 3 is an odd number? It's obvious, right? It's guaranteed to be an odd number. So what is the probability? It's 1. Okay. Now, if you want to write down the equation, yes, you can also do it. A intercept B is the same as B intercept A. And so this is by the set theory. Now, the denominator here, it is probability of A. Probability of A. Okay. So now, what is the numerator? This is probability of getting a 3. That's A intercept B, right? So intercepting, getting a 3 and getting odd numbers. So that will give you a 3. And then the probability of A, so that is getting a 3. And so that's going to give you 1. See that? So A given B and B given A, they are different. Okay, very important. They are different. Let's work on another example. There are 12 points in this diagram, and they have equal probability of happening. Right? So you count all these black dots, they have equal probability of happening. And I craft out 2 areas. The pink area is called event A. The yellow area is called event B. I want to calculate probabilities A given B and B given A. Okay, probabilities of A given B and B given A. So let's do it. Okay, so let's do it. Probability of A given B is probability of A intercept B. And probability of B, it will be the denominator. Okay, so I need some help from you guys. What is A intercept B? What is that probability? 2 over 12. Okay, that's the probability. So that's 2 over 12. Which 2? 1 and 2. So these are the 2. So it would be 2 over 12. How about B? I need some help. What is the probability of getting a B? How many? 6 over, is it 6? Okay, 6 over 12. All right, so this is 6 over 12. And so this is going to be 1 over 3. So that's A given B. And how about B given A? This is going to be A intercept B divided by P of B. And now A intercept B, I know this is 2 over 12. And then, sorry, this is A. Now, what is the size of A? 5 over 12. Okay, and so you get 2 over 5. Again, they're different. A given B and B given A, they're different. Okay, one way and the other way, they're different. Getting better? This conditional probability, not too hard, right? Okay, consider this. Let's imagine that you have a 4-sided dice. Don't ask me how I can make it. I'm not sure how I can make it. Yeah, maybe we can make it, right? Triangle, right? So you have this triangular shape, pyramid shape. You can make a 4-sided die. Okay, so let's make it. And let X be the first row and Y be the second row. So you do it twice. Let B be the event that the minimum of X and Y is 2. And M be the event that the maximum of X and Y is 3. Find B, M given B. Oh, that is harder. Okay, so we need to do some decoding here. So what does that mean? The minimum of these two numbers, like X and Y, right? So X will be the numbers from 1 to 4. Y will be the numbers from 1 to 4. Okay, it's because I'm throwing this 4-sided die twice. So I have X, I have Y. Okay, so X will be 1, 2, 3, 4. And then Y will be 1, 2, 3, 4. So I have 16 possible configurations, including 1, 1, or 1, 2, or 4, 4, and so on. Right? So there are different combinations of this pair of numbers. Now, what is this mean of x, y equals to 2 means? So I have two numbers. Okay, I have two numbers. Let's say x equals to 1 and y equals to 3. Two numbers, right? Two dice, okay? So what is the mean? The minimum of these two numbers will be 1. Okay, so that's 1. The maximum of these two numbers will be 3. Because I'm looking at the bigger of these two numbers, I'm looking at the smaller of these two numbers. So one is 1, the other one is 3. Okay, so that is the meaning of this mean of xy. This is the meaning of max of xy. All right, so now I'm looking at this event B. Event B is the event that the mean is equals to 2. What are the outcomes that can lead you to this event? Please. Bottom left corner. Aha. This quarter. This quarter. Okay, so this quarter. Okay. Will this point be, this is not part of it. Okay, it would be this, this, and that. Okay, just these two. Okay, so let's think about it. So it would be, so minimum equals to 3. So let's draw it again. 1, 2, 3, and 4. 1, 2, 3, and 4. Right? So let's call this x. This is the y. Okay, x and y. And now we ask the minimum of the two, okay, of these two xy has to be 2. The smaller is 2. Okay, smaller is 2 would be who? Well, if you choose 1 and 1, that's not good because the smaller is 1. 1 and 2, the smaller is 1. Okay, the smaller is 1. So this is not included. 1 and 3, the smaller is still 1. 1 and 4, the smaller is still 1. So 2, this corner, 2 and 1, the smaller is 1. So that's not included. 2 and 2, well, that is included. Okay, so 2 and 2 is included. 2 and 3, that's okay. 2 and 4, that's okay. Okay, are you guys following me, my logic, right? So I'm looking at this pair of numbers. This pair will be 3 and 2. The smaller of 3 and 2 is 2. Okay, and 2 will fulfill this B event, and so I give a check. This is the event of 4 and 2, and the smaller of 4 and 2 is 2, and so I give a check here. That all belongs to this event B. Okay, how about this case? This is null, this is okay, and this is okay. So you're going to get this. Now, if I flip around the color, right? So if I flip around, then you will be able to get this, the green boxes. So this is the event of B. Now, how about the event of M, where the maximum is 3? So same exercise, just flip around the logic. You can do the same. So it will be 3 and 1, so that will work. And then 3 and 2, of course, that's going to work. And then 3 and 3, that's going to work. 3 and 2, 3 and 1. Okay, so that will give you the blue boxes if you use this coordinate system. So I have found the event B. I have also found the event M. Okay, so everything has been clarified. So now let's find the probability of M given B. M given B. Without using my formula, by just looking at this diagram, can somebody tell me what is the probability of getting M given B? Yes, please. Let us go through the thinking process, right? So let's look at the denominator. Where is the denominator? B. So that would be all the checks, right? So So that would be 5 checks. 5 checks. Okay? Okay. How about the numerator? Anyone? The numerator. Yes. Yes, excellent. Okay? So the numerator would just be these two. I'm looking at a restricted space, which is defined by all the checks. Okay? Within this restricted space, I'm looking at the event that M will still happen, which are the circles. And you've got to look at the intersection of the circles and the checks. So that will give you probability of M intercept B divided by probability of B. This is going to be the probability of circle and circle and check, right? Divided by the probability of how many checks? 5. 1, 2, 3, 4, 5. 5 checks. So that's going to give you 2 over 5. So this is the probability of M given B. Now you can go home and do the same exercise and try the probability of B given M and see if they're the same. Okay? It could be the same, but just looking at this diagram, I can tell you they're the same because there is a symmetry going on here. Okay? But in general, B given M and M given B, they're not necessarily the same. But in some cases, they can be the same. Depends on how you set up the problem. Okay? Good? All right, so now let's go back and talk about a little bit theory. The conditional probability that I've been talking about here, they are legitimate probabilities. What do I mean? You can actually check the axioms, and they will apply to these conditional probabilities. Now, how do I verify that? I'm looking at this probability, A given B. Okay, A given B. That is a probability. For this to be a probability, it has to satisfy 3 axioms. Because this event B is already given to you, I sort of can just assume that it is fixed. It's already there, it's fixed. So what do I need to check? Well, the first axiom is that I need to check probability of A given B is bigger than or equals to 0. That's not negativity. Is it true? Well, of course it's true because it is the probability of A intercept B divided by the probability of B. And this is bigger than 0, this is bigger than 0. Of course, the entire thing will be bigger than 0. Right? So axiom A will be satisfied. Axiom 2 says that you're still restricting yourself to B, but then you look at the sample space. Would it equal to 1? Yeah, of course, because you're looking at probability of omega intersecting with B, and then divided by the probability of B. That is going to be the probability of B. Divided by probability of B. That's going to give you 1. So the second axiom is satisfied. How about the third axiom, which is the additivity axiom? The additivity axiom says that I consider 2 events A and C. How about that? Okay, so probability of A union C given B. Now B is always given, is always fixed, and A, C, they are disjoint. So you assume that A and C, when you take the intersection, is going to give you an empty set. So they're disjoint. Then A union C given B, this is going to be the probability of A union C intersecting with B divided by the probability of B. Okay, now I have this operation of A union C, that's a bracket, and then I intersect with B, but I can also use the set operation to do the following. The set operation says that I take this A union C, I can split it into A intercept B and C intercept B with the union sitting inside. So that's called the distributive law. And then you have probability of B. Now, you have a union of 2 sets. And since A intercept B, they're disjoint, then no matter how you intersect with B, these 2 sets will be disjoint as well. Okay? These 2 sets has to be disjoint. Now, if you're not following me, I can draw a picture to show you. So let's say you have this A here, you have this C here. They are disjoint, okay? And I can draw a set B. B, let's say they overlap with both. A intercept B would be here. C intercept B would be here. They got to be disjoint as well. Okay? So that's just a property you can easily see from the Venn diagram. So since they're disjoints, then the additivity law will apply. And so you will have probability of A intercept B plus the probability of C intercept B divided by the probability of B. Okay? And that is axiom number 3. And so now I divided by the probability of B, so I will get probability of A given B, and then I have probability of C given B. And now let's go all the way back here. In the very beginning, I showed that this union, A union C, and they are disjoint sets, I can get this probability of A and probability of C, everyone conditioned on B. Okay? So again, I can verify the third axiom. So all the axioms are verified, and therefore this is a legitimate probability. Okay? So whenever you are conditioned on certain events, as long as that event is fixed, everything else you do is a legitimate probability. So you can sum everything, you can get to 1. Now, do not confuse, okay, that if I have this probability of A, okay, let's say AIs, okay, and then condition on B, let's say that okay, I think let's talk about this later on, okay, a little bit later. When we talk about the Bayes theorem, then we can go back to this point to show you something. Okay, so I will save for that. Okay. Any questions so far? No. Okay, good. So let's move on to this chapter 2.5 on independence. Now, I just want to remind you that this chapter 2.4, 2.5, and 2.6, they're all together. Okay, try not to separate them individually. They're all together, and each of them, they are very, very small, very, very short. But then when you start to combine them, things will become more and more difficult. Okay, so we'll spend more time as we are going to 2.6, and then as we are seeing more difficult examples, we'll spend more time on that. Independence. Let's talk about independence. Okay, so what is independence? Let's think about this following example. Okay, so you throw a die twice. The first die is 3, the second die is 4. Are they independent? Now, of course, I haven't defined this notion of independence. But we can always try to associate this concept of independence with our daily experience. You throw the first die, you throw the second die. The first die is not going to interfere the second die. The second die is not going to interfere the first die. They're just separated. Okay? They're not interfering with each other. Yeah, okay, they're independent events. Okay? They're not going to interact with each other. Now, that's a little bit loose definition of independence, right? But I guess we will agree that if they're not influencing each other, they shouldn't have any dependency, right? One shouldn't depend on the other. Okay, so what is independence? Are they independent? How do we define that? How do we define that? Now, the concept of independence has to build on top of this conditional probability. Why? The conditional probability is about 2 events. Okay? Event A and event B. Given that B has happened, what is the probability that A will happen? How do you define independence? Well, if B has happened, the probability of getting A has nothing to do with B. Then I say A and B are independent. Okay? So let's say what would be the good example here? I drink water. Okay, so that's event A. And B is I drive my car. Okay? All right, so these are not very good examples, but we can continue, okay? So event B is that I drive my car. Event A is that I drink water. Regardless whether I'm driving a car, the probability that I'm going to drink water will still be the same probability. Okay? My car is not too dry, not too bad. Okay, so that's the probability, right? So I drive a car and then I drink water. That's independent. Give you another example. On I-65, okay, we're all familiar with I-65. The probability of seeing a Lamborghini, give me a number, probability. Some percentage, some, in West Lafayette region. Some probability, seeing a Lamborghini. Some number, okay, non-zero, obviously, non-zero. No, that's event B. Event A would be the driver is an undergraduate Purdue student. Okay. So event B is that there is a Lamborghini on I-65. Event A is that the driver is a Purdue undergraduate student. Both are non-zero. Are they independent events? No. Someone says no. Why do you think it is no? Right. So there could be the possibility that Purdue undergraduate students are driving Lamborghini. Now, how about Purdue graduate students driving a Lamborghini? Their probability is usually lower. Now, what is the probability that a Purdue faculty would drive a Lamborghini? That's even lower. Okay, if you have a family, you have kids, the chance that you're going to drive that kind of car is zero. Okay, just look at me as an example. Okay, so there is certain level of dependency. There's certain level of dependency over there, and so one event that you observe will have certain connection with another event. We call it dependent. Okay, but this kind of concept is usually vague, right? It's intuitive, but that can lead you to some mistake. And so we need a little bit more formal way of defining the independence, and then we can go back and check whether our intuition makes sense. And sometimes it's not that easy to verify. Let's go to the this example. Okay, you throw a die twice again, right? So now in the previous example, one is 3, one is 4. Getting a 3, getting 4, of course, there's no interaction at all. No interaction at all. But in this case, the first die is 1. The second die, the second event is that the sum is 7. The sum is 7. Okay. Now, if one is 3, one is 4. Of course, it's so clear. But here, the event A is that the first one is 1. The second event it is sum is 7. Now, event B, of course, has to take into account of both the first die and the second die. And so the calculation will be a little bit more messier. Do you think that these two events, they are independent or not independent? Anyone want to make a guess? Are they independent events or are they dependent events? I would say it is dependent, but just looking at the description. But will anyone say that it is independent? Yes, please. There is always a possibility that the sum is 7, it will be 1 and 6. There are only two possibilities, 1, 6, and 6, 1. Right? So it's 1, 6, and 6, 1. Or 1 over 6, over 6. So we're getting to thinking about the probability. We're thinking about the number, right? Okay, so why don't we sit down and do some calculation, very simple calculation. What is the, what are all the possible cases of getting B? What are all the possible configurations that can lead you to B? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. 6 cases. Okay? they can all give you sum to 7. Right? One is listed here. You have 6 configurations that can give you this. Okay? All right, so that is the event. And so now the probability, okay, the probability of getting a B is 1/6. We can calculate that. The probability of getting the first die being 1, what is that? This is 1/6. Okay, it's not 1/36 because the first die is 1. I have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1/6. So that's 6 configurations out of 36 possible cases. So this is 6/36. That's 1/6. Okay, so A and B. How about probability of A given B? Probability of A given B. Anyone want to try? You want to try that? Oh, let's do it. So probability of A intercept B divided by the probability of B. Probability of B, of course, is 1/6. What is the probability of A intercept B? Now, we need to draw a figure to clarify, right? So let's don't mess up. Let's draw a figure. So this is 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. So this is the first. This is the second. Okay? So now let's look at the event A. The event A would be here. This is A, because the first die is 1. It's always 1. Event B is that it is sum equals to 7. Sum equals to 7, it will be here, 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 and here. Okay? So the probability of A intercept B is 1/36. So you have this number is 1/6. Okay, so we're right. Okay, so the A given B is 1/6. How about probability of getting an A? Let's go back. Wait a minute, they're the same. Probability of getting an A is the same as the probability of getting A given B. So regardless of whether B has happened, the probability of getting an A is always 1/6. Okay? It's always over 6. In fact, you can also check that the probability of B given A, okay, probability of B given A, so this is going to be A intercept B divided by the probability of A. This is also 1/6. Meaning that if A has happened, if I know that the first die is 1, the probability of getting sum equals to 7 is 1/6. It's independent of what A has happened. Okay. So it turns out that these two events, they're independent because regardless whether A has happened before or B has happened before, the probability of getting the other event, the probability is not changed. The probability is not changed. So let's look at the definition first, okay? I know you have a lot of questions, yeah. So let's look at the definition first, and then we can come back and see whether intuitively it makes sense to have this kind of setup. Does it make sense, okay? So how do we define independence? We say that the two events, A and B, they are statistically independent if probability of A intercept B is probability of A times probability of B. Now, I claim that this is going to be the same as your conditional probability because if you move probability of A to the left-hand side, or you move probability B to the left-hand side, you're going to get probability of A intercept B divided by probability of B equals to probability of A. And this is the probability of A given B, right? So you see that this statistical independence really means that probability of A is the same as A given B. So B has no influence to the probability of getting an A. Okay, I emphasize this is a probability. That number is not changed, whether you have this condition on B or not. Independence is also different from disjoint. Can anyone tell me why? Disjoint means, let's say A and B are disjoint. What do we have? Let's look at the probability. Probability of A intercept B. If they're disjoint, what do we get? They don't overlap at all. Therefore, the intersection will be anti-set, and therefore the probability will be 0. Okay? So disjoint means that probability of A intercept B will be the probability of an empty set, so you get 0. That is disjoint. How about independent? Well, independence means that this product, right? You have this A intercept B. You can factorize into probability of A and probability of B. You can factorize it. Now here for disjoint, you cannot factorize. Okay? You're not talking about the factorization. You're just looking at the empty set. Right? So disjoint and independence, they are completely different. And every year, every semester, we have students get confused about disjoint and the independence. Independence is a statistical property. Okay, it's a statistical property that talks about the probability, that the probability of an intersection can be factorized. Disjoint is a set problem. Disjoint, okay, it's a set problem. It means that the two sets, when you take the intersection, they're empty. That's called a disjoint. Okay, one is a set operation, the other one is a probability operation. So this we have already gone through. Okay, so independence via conditional probability, A given B. So you have this ratio of A intercept B and B probability. And so if the independence, you can write this, and therefore if you have A intercept B equals to A, we say that they're independent. Okay? So the interpretation is pretty easy. The presence or absence of B has no influence to A. Okay, so examples, but I guess the time is running short. So rather than rushing through all the examples, maybe we can take a pause at this point, okay? And then we can come back. Now I will talk about two things on the next lecture. One is to give you examples, and then I'm going to give you some intuition. I'm going to come back to this point. Why would the sum equals to 7 thing being independent? I will go back to that example. Okay, and then I will also talk about the space theorem, and then I'm going to talk about more examples of how do you use this independence to solve more meaningful problems. Okay, so be prepared that there will be more examples coming on the next lecture. Okay, so I will see you next time.